So it's time. Let's record this class. Emma, you can go first.
Okay, thank you.
You're welcome.
Okay, can you see this?
Yep.
Okay, so an urn contains 6 white balls and 9 black balls. If 4 balls are randomly selected without replacement, what is the probability that the first 2 selected are white and the last 2 are black? So I set up a division. So first I did the white balls, so 2 white balls from the 6, and then I did 2 black balls from the 9 black balls. So I separated them like that, and then on the bottom I did 2 white from all, and all of them were 15 because 9 plus 6. And then I subtracted 2 because the first 2 were going to be already selected and not replaced. So then I would do 2 from 13. And then below for me, it's easy to see when I do like 6 times 5 over 2 and then 9 times 8 over 2 times 1 and stuff like that. So then I multiplied, I got 540 divided by 8,190, which I simplified to 6 over 91.
Okay, I have a question.
Yeah.
I don't think I'm understanding you.
Sure.
So out of 6, right, out of 6 you choose 2 because you need the first 2.
Yeah, white balls.
First 2 to be white and last 2 to be black. So
right.
9 choose 2. So I just don't understand your notation. You have out of 6 choose 2, then you have 2 white from 6. Or that's your own explanation.
Yeah, that was just for me to help myself like understand it in my head.
Oh, okay, got it. So
two
basically
white,
out of 6.
6 white, yeah, and then 2 black from the total 9 black balls.
Okay, so you're multiplying those 2, right?
Yeah, exactly.
Okay, the denominator is out of 15, choose 2. Out of 15, 2 white from all. Then so 13 left. Out of 13, choose 2 black from. Oh, okay, now I understand.
Yeah.
Okay, then you calculate. Okay, all right. Anyone else has any questions? All right, Emma, thank you.
Thank you.
I'm going next. My question is, a couple has 2 children. What is the probability that both are girls if the older of the 2 is a girl? The sample space is here. And the probability of 2 are girls is this one, G and G, 1 over 4. And the older one is a girl. It's either G or BG, so it's going to be 2/4. And the probability of both girls and the older one is a girl is 1 over 4. It's this one, the same as 2 girls. And the probability of probability of both are girls if the older one of 2 is a girl is on the probability of A and B divided by 2 over 4. I get 1/2 as a result for the probability both are girls if the older one of the 2 is a girl.
Okay, I like your notation. When you name probability of 2 girls A, that's an even A. The older of 2 is a girl, you name the B. You find the intersection of the probability of the intersection of those 2. Then conditional probability is probability of conditional. Okay, so this is P, probability of A and B divided by probability of girl. Probability of older one is a girl. I see. So it's half. It's 50%, huh? Okay. All right. Anyone has any questions? This is good. This is good because we talked about this last class. It's a good review for everybody. All right. Anyone has any questions? Great. This is how.
Hi, Professor.
Hello.
So I'm presenting question 2 from chapter 3.
Okay.
Okay, so lobsters are caught in morning and afternoon sessions. The number of lobsters that can be caught in each session are 0, 1, 2, 3, 4, or 5. Each probability is 1 over 6. Find a probability of at least one lobster being caught in the afternoon, given that more lobsters were caught in the morning. So from all these outcomes from 0, 1, 2, 3, 4, 5, with each probability is 1 over 6, we have all the outcomes, probability of all the outcomes is 1 over 36. But the question is asking us to find the probability of at least one lobster that being caught in the afternoon, given that more lobsters are caught in the morning. So I list that as event A with more lobsters in the morning, which give us that we have 15 outcomes in here. And then for event B, we have at least one lobster caught in the afternoon, but we also need to include that more lobsters were caught in the morning. So we have probability that event B happens is 10 outcomes. So once we list this out as probability of event B occurred given that A has occurred is 10 over 15 equals 2 over 3.
Great. Great. Yeah. Great. I like that you use this way. Looks like ordered pairs. Great. If anyone has any questions, feel free to ask. So those are good. Good.
Can I see my screen?
Oh, hold on a second. Yes.
This is question 9. Consider 3 urns. A contains 2 white and 4 rebels. And B contains A white and 4 rebels. And urn C contains 1 white and 3 rebels. If one vote is selected from each urn, what is the probability that the votes chosen from urn A was white given that exactly 2 white votes were selected? Since we gotta use the conditional probability here, denote the first event to be A, and the second event, and the second event to be B, and we're looking for those two values. We know that the sample space would be 6 times 12 times 4 because we have 6 choose 1 from A and so forth. And then for the event of A, we have 3 cases. The first cases would be red, white, white, and then white, red, white, and then white, white, red. Then we have total 88 cases out of 288. For the event of BA, we have the complement of the first bowl is not white. That would be 88 minus 32. So we have the event of BA is 56. And then we just plug into this formula. And that will be the final answer.
Okay, you can keep simplifying this, right? Simplifying to the simplest form.
Oh.
It can be divided by 4.
By 8.
Oh, can be divided by 8, actually.
So that would be 7 over 11.
Exactly, yeah. Great, great. Okay, one more thing. So for us, so this is not about convention. This is your own notation, like a E of A. A itself is an what do you call it? Event. But by convention, we don't use E of A to represent that. Just for you to know.
Okay.
Okay, but great, thank you. Anyone has any questions? Great. Whose work is this?
This is my
Oh, Tom.
problem.
Okay.
Yep.
56?
Yeah. So for this problem, we're given 3 spinners, and we're to find out whether person B has a better strategy than person A, where person A can choose a spinner, and then person B can choose a spinner after them. It works by each player has one roll of the spinner, so they get one number, and then the person with the number that rolls higher wins. So for this question, basically have an array of 3 values for each spinner, and there's 9 outcomes based on whichever spinner person B chooses. For example, like person A could choose spinner A, and then he might land on a 1 with a 1/3 probability, and person B might land on a 8 with a 1/3 probability. So by sort of numbering the ordered pairs you could get with each of them, there's 9 outcomes, and for each spinner there's a spinner with it that has a 5/9 chance of winning by just counting the number of ordered pairs where they would win. So it ends up being that player B can choose a superior spinner with a 9/5 or 5/9 probability to win, based on whichever spinner person A chooses. And since this problem only had like three numbers for each spinner, I also did like an algorithm to find like if it was any number of elements. Say the spinner had like 10 elements, then you'd have to manually check like 100 ordered pairs, which would basically be like you'd have to check n squared number of possibilities. So
right.
For like a general solution, I basically gave like a programming solution where you could check the maximum of the arrays, and if the first maximum is greater than the second array's maximum, you could add up, you could count up all of the elements in the second array into a counter and just keep popping out the maximum of the arrays until you reach an array that's empty. So instead of counting like n squared number of ordered pairs, you would only need to count like n terms. But that was just something I did on my own.
So are you computer science majored?
Yeah, I work in software.
Oh, you already? Oh, okay. All right. Yeah. No wonder. All right. Anyone has questions? All right. Thank you, Tom. Okay, so Catherine went, Emma went out, Jay, Tom. So we have Xiu Yu. and Yinping. So you two left. Anyone else like to present today? All right, Yinping is up.
Can you see my screen?
Yeah.
My question is, in chapter 3:11, is two cards are randomly chosen without replacement from an ordering deck of 42 cards. Let B be the event that both cards are aces. Let AS be the event that the ace of spades is chosen, and let A be the event that at least one ace is chosen. Find A. For question A, the probability of event AS is 1 multiplies 51 over total probability, since there are only one ace of spades in a deck of cards. And choose another card from the remaining 51 cards is equal to 1 over 26. And for the probability of B intersect of AS, it choose one ace of spades and choose another ace from the remaining sorry remain three aces cards is equal to 1 over 442. Based on the formula, the probability of event AS occur in order of B to occur is PAS over PBAS. The answer is 1 over 17. And for question B, we need to find PA and PAB. Event A is at least one ace is chosen, so there are two cases. Only one ace is chosen. Choose one ace from four aces in a card, and choose another one from the aces cards. And the other case is both two cards is ace. That's just PB. PB is choose two cards from four aces over total probability is 1 over 221. Add these two cases, we can get PA is equal 33 over 221, and PAB is just equal to PB. The probability that event A occurs in order of B to occur is PAB over PA is equal 1 over 33. And that's it.
Okay, I just don't see your notation of for A, P.
Question.
Yeah, P of B, B occurs after AS occurs. I just don't see that one somewhere, anywhere. This is another line. I don't know if you see my cursor. Okay, 1 over 17. What's before 1 over 17? Something's missing. Maybe that doesn't show on my screen.
Let me see. What's that?
What is the numerator?
My answer is. Let me see.
Right. I was thinking, right, something's here.
Oh, 1.
Oh, 26. Oh, hold on. Right. Oh, right. Over 1 over 400. Okay, now it makes sense. You have an equal sign in between. Okay. All right, great. Anyone has any questions? Okay, great. Good review for previous one. So showing.
Good evening, Professor.
Good evening.
Can you see my screen?
Yes.
Okay, so I'm gonna present the question 47 from chapter 2. So the question is, suppose that 5 of the number 1, 2 through 14 are chosen. Find the probability that 9 is the third smallest value chosen. So from the question, we know that 9 is the third smallest value. That means they still have two smallest value that's more than the 9. So we need to choose two number from the 1 to A, which is A choose 2. Then 9 is itself, so it's 1 choose 1. Then we still have two numbers left, which is choose from the 10 to 14. So it's 5 choose 2. And the sample space is 14 choose 5 because we need to choose 5 number from the 14 number. Then the probability that 9 is the third smallest value chosen is equal to these 3 times together to divide the sample space. Then make a calculation. We will get 20 over 143.
Perfect. Great. Nice. Right. So this is very clear. Okay. Some of you, when you write, I hope you can write like 秀语. Okay, right this way. It's so clear to see it. So I don't have to, go here and there to look for it. So this, okay, great. Anyone has any questions? All right, thank you. Let me give you credits. And then, anyone else like to present? All right. Oh, Angela, you like to present? Let me make you presenter. Okay, go ahead.
Hi.
Hello.
Anyone did 28 or no?
I'm sorry.
Did anyone do number 28?
I don't remember anyone did 28.
Okay.
A newly enacted law may finally allow you to hold your abuser accountable, no matter how long ago the abuse occurred. New York State has recently passed legislation which, for the first time, allows survivors of adult sexual abuse
Chapter
a limited
3.
look-back window to hold their abusers accountable once and for all. But these temporary laws will expire soon, and time is quickly running out. Don't wait until it's too late. If you were
How is the clear record of it?
committed by an OBGYN, urologist, dentist, chiropractor, dermatologist, or within any professional organization by a position of authority, these new laws can provide a path to justice and may entitle
Alright.
you to significant.
It says suppose that 5% of men and 25% of women are colorblind. A colorblind person is chosen at random. What is the probability of this person being male? So given that the person is male and colorblind, we're trying to find a colorblind male. So we would divide it by colorblind male multiplied by a male plus a colorblind female multiplied by a female. So since 5%.
Okay, your first line missing a slash.
Oh, okay.
Before this, right?
Yeah.
Okay.
So 5% is 0.05, and we multiplied by 0.5 because we are saying that it may be 50% male, 50% female, and then we put it over the same thing again and add the 25% of women and multiply by 50%, and the probability of the person being male is 95%.
Wow, pretty high, huh?
Wait, no, that's too high.
Yeah. How did you do this question? I mean, how or Jie?
What you said, sorry?
Anyone else did this question? Can anyone confirm his answer? Okay, Andreli. 1, 2, 3. 3 people did not agree with you. So what was your answer? How
Professor, I
Catherine
think
and
they said that they didn't do this questions.
Oh, you didn't do this question. Oh, no means you didn't do this question. I mean, anyone has any different answers from him? Too far away. 28. And Julie, can you put up again?
All right.
Yeah, how agree with you? 95%. To me, I'm just thinking.
I'm just
95%.
answering this question.
Oh, all right.
Chapter 3.
Yeah, you put it back up again. Let's see. 5% of men and 5% of men and 0.25% of women are colorblind.
Oh, yes, because
Then
0.25 is less than 1%. So
right. So a colorblind person is chosen at random. What is the probability? Oh, okay. Because the sample space is small. Okay. What is the probability of a person being male? I see. I got it. So that makes sense.
yeah.
Yeah. Oh, hold on a second. Hao said he checked the answer. He says check the textbook answer is 20/21.
Yes, then 20/21 is
right, 20/21,
95%.
right. It's high, it's about 95%, yes. Okay, thank you.
No problem.
Thank you, Andreli. Yeah, but conditional probability sometimes is tricky. It's not go with our intuition. My intuition for that question was, oh, this seems too high. But then you look, oops.
I went,
What did I do?
I did a later question because I normally bring a question that someone has done before. So.
Oh, okay. Thank you.
Yeah.
Thank you. It's a good question. Yeah, because the conditional sample space, because the denominator, the sample space is it's like limited. It's a current sample space. It's a conditional sample space. So I went back to look at the question. The sample space is really small itself. All right. So today we're going to talk about something called the Bayes formula, and it's very famous. All right, chapter 3, section 3. So E and F events. So we express E as this. So E can be written as intersection of E and F, unit intersection of E and the complement of F, of course, right? In order for an outcome to be in E, it must either in both E and F, or be in its unit, or be in E and the complement of F. Because intersection of E and F and E and the complement of F are mutually exclusive. That because F and its complement are mutually exclusive. Then we can write probability of E like this. So that's probability of intersection of EF and plus probability of the intersection of E and the complement of F. Then we use this conditional probability formula. So we get this. Right. Then what else? So this one, then we can use the complement. So what is the probability of complement of F? That's 1 minus probability of F. So this will arrive this formula, probability of E equals to probability of E after F occurred multiplied by probability of F plus probability of E after the complement of F occurred multiplied by the probability of the complement of F. So what does this equation tell us? It states that the probability, even E, is a weighted average of the conditional probability of E given that F has occurred and the conditional probability E given that F has not occurred. Each conditional probability being given as much weight as the event on which it is conditioned has of occurring. This is an extremely useful formula because it often enables us to determine the probability of an event by first conditioning upon whether or not some second event has occurred. That is, there are many instances in which it is difficult to compute the probability of an event directly, but it's straightforward to compute it once we know whether or not some second event has occurred. So we can illustrate it with this Venn diagram. Yeah, I'm trying to remember this myself too. Okay. So let's see this Venn diagram. So E and F. So E intersected with F is this part. E intersected with complement of F is this part. So union of those two, that's E. Let's see example 3a. An insurance company believes that people can be divided into two classes, those who are accident prone and those who are not. The company's statistics show that an accident prone person will have an accident at some time within a fixed 1 year period with probability of 0.4. Whereas this probability decreases to 0.2 for a person who is not accident prone. If we assume that 30% of the population is accident prone, what is the probability that a new policyholder will have an accident within a year of purchasing a policy? We shall obtain the desired probability by first conditioning upon whether or not the policyholder is accident prone. So we denote A1, the event that policyholder will have an accident within a year, which is accident prone. And the letter A denote the event that policyholder is accident prone. Then the desired probability is given as, so probability of the policyholder will have accident within a year. So basically we use the formula, right? So probability of this A1 after A occurred. So this person is accident prone multiplied by probability of accident prone, then plus the complement part. Okay, and so these numbers are given. So within a year, probability accident prone is 0.4. Then 30% of the population is accident prone. So probability of A. Then plus the complement part, which is given. So 0.2 if it's not accidental prone. and multiply by 1 minus 30%, which is 70%, which is 0.7. Not accident prone. So add those two numbers, we get 26%. All right. Anyone has any questions? Yeah, it will be difficult, right? Any other way to find the probability of, the policy holder will have an accident within a year. Okay, let's see. So that's part 1. This is part 2. Suppose that the new policyholder has that accident within a year of purchasing a policy. What is the probability that he or she is accident prone? Okay, so the condition, so something happened, or is this? So he had accident, which is A1, right? After A1 happened, and then so he's accident prone. He's accident prone. A. So probability. So the desired probability is after A1 occurred, yeah, the policyholder had accident within a year, and we want to find out the probability he or she is accident prone. So that equals to probability of the intersection of those two, accident happening in a year and he or she is accident prone, and divided by probability of accident happened in a year, within a year. So this one, the numerator, we get intersection, which is probability of, we could use this one we know already. A1 after A happened, right? Accident prone, and accident happened in a year. So I have to come back to check. Yeah, 0.4. Then multiply by the probability of accidental prone. Accidental prone is 30%. So 0.4 times 0.3 in the numerator. Then probability of accident happened within a year, which is this guy. We found out 0.26. So it simplifies it to be 6 over 13. Just make sure your final answer is the simplest, in the simplest fraction form. Okay, anyone has any questions? Let's see this 3b. Consider the following game played with an ordinary deck of 52 playing cards. The cards are shuffled and then turned over one at a time. At any time, the player can guess the next card to be turned over will be the ace of spades. Ace of spades again. If it is, then the player wins. In addition, the player is said to win if the ace of spades has not yet appeared, when only one card remains. Oh, okay, which means the last one is ace of spades, right? And no guess has yet been made. What is a good strategy? What is a bad strategy? Every strategy has probability 1 over 52 of winning. To show this, we will use induction to prove the stronger result that for the N card deck. Like Tom like to do. Extend 52 to N cards. So one of whose cards is the ace of spades. The probability of winning is 1 over N. No matter what strategy is employed, since this is clearly true for N equals to 1. Okay, so induction, right? We need to take three steps. So everyone knows that, right? So we do N equals to 1. So this is a base case. Assume it to be true for an n-1 card deck, and now consider an n card deck. So the second step is assuming assumption. Assume n-1 step is true. So that's assumption, the second step for induction. Then we need to prove for n. Right. So induction steps have 3 steps. Induction proof has 3 steps. We do the base step. We usually, let n equals 1, whatever the variable is. Then we assume n-1 to be true. Then we use this to prove n is true. The case of n is true. We can fix any strategy and let P denote the probability that the strategy guesses that the first card is ace of spades. Given that it does, the player's probability of winning is 1 over n. If, however, the strategy does not guess that the first card is the ace of spades, then the probability that the player wins is the probability that the first card is not the ace of the spades, namely n-1 divided by n. So the rest of n-1 cards. So multiply by the conditional probability of winning, given that the first card is not the ace of spades. But this latter conditional probability is equal to the probability of winning when using n-1 cards containing a single ace of spades. It is then by the induction hypothesis, so 1 over n-1. Hence, given that strategy does not guess the first card, so the probability of winning is n-1 divided by n times 1 over n-1, which equals 1 over n. So letting G the event that the first card is guessed, so we obtain probability of winning equals to probability of winning after G happened. G means, the first card is guessed already. The first card is done. Plus P of winning, after the complement of G, the first card is not guessed. Right? The multiplied by the probability of the card is not guessed. So I have n1 over n multiplied by P. Remember P is, so P denote the probability that a strategy guesses that the first card is the ace of spades. Okay? And then first one is not, that's 1 minus P. So adding those two, that's still 1 over n. Okay, so that's to prove. Right, so that's same thing for 1 over 52. That's n equals to 52. Anyone has any questions? All right, let's see example 3. C. In answering a question on the multiple choice test, the student either knows the answer or guesses. Let P be the probability that the student knows the answer, and 1 minus P be the probability that don't. Assume that a student who guesses at the answer will be correct with probability 1 over m, where m is the number of multiple choice alternatives. What is the conditional probability that a student knew the answer to a question given that he or she answered it correctly? All right. So let us correctly, the C and K denote respectively the events that a student answered the question correctly and the event that he or she actually knows the answer. Okay, so K knows the answer, C is answers correctly. So that equals the probability of intersection of answers correctly and she knew the answer. and divided by probability of correct. So then intersection of probability of intersection of K and C is conditional. Probability of correctly after, because she knew, multiplied by the probability she knew the answer. Divided by the denominator, we use the previous 3.1 equation equals the probability of he answers correctly because she knew, multiplied by the probability she knew, plus the complement part. Right. So then the numerator probability she knew P be the probability that they know the answer, right? So that's P. What's the probability of she answers correct? She knew the answer, you know, she chose correctly. That's 100%, I guess. Then that's P. Then this is right. So this, oh, this is the same. Because those two are the same. You see this one and this one are the same. P. Then this one is the complement, right? The complement, and this complement is 1 minus P. So this one is she, you know, he doesn't know, she did not know the answer, but she chose correctly. So he guessed it. So he guessed, and we are given the probability is 1 over m. Is 1 over m. So we have this 1 over m multiplied by 1 minus p. Then we simplify, so we get this answer. All right. Anyone has any questions? The only tricky part is this one. Probability of, you know, he knew the answer, he chose correctly. Right. It's 100%. For example, if m equals to 5, p equals to half, then the probability we can substitute in to get 5 over 6. Okay, anyone has any questions? All right, let's see next one. D. A lab blood test is 95% effective in detecting a certain disease when it is in fact present. However, the test also yields a false positive result for 1% of the healthy persons tested. That is, if a healthy person is tested, then with probability 0.01, the test result will imply that he or she has the disease. Anyone created a group chat for this class? If 0.5% of the population actually has the disease, what is the probability that a person has the disease given that the test result is positive? A lot of work is decoding, right? A lot of work is decoding the meaning of those, you know, data. What does 95 represent in terms of events? What does 0.01 represent? What does 0.5 represent? And 1% represents, right? Once you are able to decoding these numbers, write in a notation of a probability of things, the rest is just using the formula. Okay, what is the question of this one? So if 0.5% of the population actually has the disease, what is the probability that a person has the disease given that the test result is positive? Okay, so D is the event of the person tested has the disease, and the E, the event, the result is positive. So we want to find out the probability a person has a disease that the test result is positive. Okay, so D happens after E already happened. So the formula is probability of the intersection of those two divided by probability of test results positive. But we don't have those two data, right? If we decode in the ones we have here, so we don't have it. So we could write down each one represent, right? Then that means we have to use formula. We have to use the formulas. So probability of the intersection D and E, right, equals this probability of the test result is positive, you know, and the person was tested effective, the person was tested with the disease, and the result is positive. Multiplied by the probability of the result is positive, which is this one we have, right? Those two we have. We have 0.5%. First, we have this. We have 95% positive result. We have 0.5% actually has a disease, right? So the numerator we have, then denominator. So this one is the same as the numerator. We just have to calculate this part. And this part, the probability of this one, which is 1 subtract 0.05. Probability of this one is somewhere, it's here. It's 1% of a healthy persons tested. False positive is false. Then the rest is just calculation. So the work happens just in here, right? Those two steps to decode the information, to name the events, decode the information from the settings. Anyone has any questions? You see this one is similar to see this one, similar to D. Let's see this one. Okay, they're all similar. Yeah. Okay, so they're all similar. I'm going to skip those examples, all right? So you go through the examples yourself. Let's go to this one. So definition, the odds of an event A are defined as this. Probability of A over probability of the complement of A, all right? So that's just a term, the odds. The odds, what's the odds? The odds is the probability of an event divided the ratio of the probability of an event with its probability of its complement. Of course, it's always a P of A divided by 1 minus P of A. Right? That is the odds of an event A tells how much more likely it is that the event A occurs than it is that it does not occur, because it's a ratio of those two. For instance, if probability of A is 2/3, then probability of A equals to 2 multiplied by a probability of its complement, because its complement is only 1/3. So that means so even A is more likely to occur. Let's read this. Consider now a hypothesis H that is true with probability of H, and suppose that the new evidence E is introduced. Then the conditional probability given the evidence of E that H is true, that H is not true, are respectively given by this. So conditional. That's P intersect H of E divided by P of E. So P intersection of probability of intersection of H and E, it can be this probability of E happened before after H happened multiplied by P of H. And also you can write this, so for the complement of this. So then if we divide those two, so the odds of this is, can we simplify this? Something is simplified. Yes. So this is a simplified. Probability of E is simplified. The probability of H divided by its complement, probability of its complement, and the probability of this with its complement. 3.3. This is a cool result. You see that? Okay, I hope you see the symmetry here. All right. Let's see how we use this. So that is the new value of the odds of H is the old value multiplied by the ratio of the conditional probability of the new evidence, given that H is true, to the conditional probability given H is not true. Yes. Okay, a group chat is made. Yeah, group work is important. Okay, let's see an example for that. Because I want to reach Bayes' formula. Position. I think I missed it. Okay, let's see if we can get up to here. So let's see an example I. Anyone has any questions? Okay. Okay, let's see this question I. An urn contains two type A coins and one type B coins. When the type A coin is flipped, it comes up heads with probability 1/4. Whereas when the type B coin is flipped, it comes up heads with a probability of 3/4. Right? So it'll be a good idea, when we read this, we denote the event. A coin is randomly chosen from the urn and flipped. Given that the flip landed on heads, what is the probability? What is the probability that it was a type A coin? So we let A be the event a type A coin was flipped, and B is the complement of A be the event that the type B coin was flipped. And we want probability of it's a head flipped happens to be a head, and the event is A, and it comes from A coin, right? So the heads up one is a A coin. Where heads is the event that the flip landed on heads. Okay, so from equation 3.3, the one we just, this one. So what is the probability? What is the odds of that happens? So basically probability of it's a heads and a coin, and it's a heads, the denominator is a heads of B coin. So using that as the probability of A divided by probability of B, and then probability of, it was a coin and it has a, it's flip a coin and it's head, it landed on head. Divided by flip on B coin, it landed on head. And these ones were given, right? Probability of A, it comes up heads with a probability of 1/4, right? That's this one. And it's a B coin, heads up with 3/4. B heads, that's 3/4. What is the probability of A? How many we, so two type of A coins and one type of B coin, right? So 3 coins. So probability of A is 2/3, probability of B is 1/3. Then we do the calculation, we get 2/3. So what's the probability that it was a type of coin? So if flip a coin, if it landed on head, and the probability is from A is 2/3. Is this a coincidence? Because the odds is the same as this. We have, okay, there has to be a coincidence. Hence the odds are 2/3. 2/3 to 1, or equivalently 2/3 ratio to 1. If we do the calculation, the probability is 2/5 that the type A coin was flipped. Oh, okay. Because this is the odds is this, right? The odds is this, the formula. Okay, equation 3.1 may be generalized as to n case n events. Right? If the sample space is the unit of all those n events, and exactly one of the events must occur by writing the event equals the unit of the intersection of, intersection E with some of these F's, right? So one of them must occur, so intersect with E. And using the fact events E are mutually exclusive. Okay, E are mutually exclusive, so we have this 3.4 formula. So this is up to n events for F. Okay, Bayes' formula. Bayes' formula. So F is still the F from above. Think about it, we have n events related with F. Intersection from this from another formula. All right. I don't know how you remember this, right? But I think you can make sense of this. Okay, so this equation is known as a Bayes formula. So we think of events Fj as being possible hypotheses about some subject matter. Then Bayes' formula may be interpreted as showing us how opinions about this hypothesis held before the experiment was carried out. That is, the probability of this such event should be modified by the evidence produced by the experiment. I don't know if that makes sense to you. Let's see examples. Example always make better sense. A plane is missing, and it's presumed that it was equally likely to have gone down in any of the three possible regions. So let 1 minus beta I equals 1, 2, 3, denote the probability that the plane will be found upon a search of the ith region when the plane is, in fact, in that region. So the constants beta I are called overlook probabilities. Overlook probability because they represent the probability of overlooking the plane. So they are generally attributable to the geographical and environmental conditions of the regions. What is the conditional probability? That the plane is in the ith region, given that the search of region 1 is unsuccessful. Okay, given that region 1, the search of region 1 is unsuccessful. Okay, we denote Ri, I equals 3, 1, 2, 3, be the event that the plane is in region I. So the plane is in region I. And then the search of region 1 is unsuccessful. And let E denote that. Denote, okay, a search in region 1 is unsuccessful. So we want to find the probability of Ri, given that E already happened. So that equals to the probability of the intersection of those two divided by probability of E. And the intersection of those two equals to probability of region 1. It happens in region 1 multiplied by the probability happening in region 1 and the event, the region, and is not successful, is unsuccessful. This is the intersection of those two. Then divided by probability of E, probability of the event of a search in region 1 is not successful. So search in region 1 is not successful because we have 3 regions. We add up all those 3 regions, the probability of E after R1, R2, R3, region 1, region 2, region 3, in region 1, in region 2, in region 3. And with the search in region 1 is unsuccessful. Then multiply by the probability of the region. So given this way, we give this 1 minus beta I. So the first one, well, we have 3 regions, so that each one is just 1/3, right? Found in each region, probability of region 1 equals the probability of region 2 equals the probability of region 3, that's just 1/3. and region 1, in region 1, and the event under region 1 is under the research, and the search in region 1 is unsuccessful. That's a mouthful. Because 1 minus beta I, or 1 minus beta 1, denotes the probability that is found in the region, right? So that means the complement is BI, beta I. So complement is beta I, beta 1 here. Then similarly, the first one is the same as the numerator. Then the rest of the two is 1/3, right? In region 2, think about this in region 2, probability of region 2, 1/3. Then probability of found in region 2, but not in region 1. Of course, it's 1, right? If you found in region 2, it will not be in region 1. So that's 100%. Same thing for 3. Found in region 3 and will not be in region 1. Only thing is the first one different, right? In region 1 and not found in region 1. So do the calculation. So in the end, you'll get this beta 1 divided by beta 1 plus 2. Anyone has any questions? I think most of the work is just to denote, use the right, for j equals to 2 and 3, right? So that's for 1. Will be similarly for 2 and 3. So that's one of the examples using Bayes' formula. Let's see some other examples. Let's see this one. Oh, this one. Okay, this one is good. Suppose that we have 3 cards that are identical in form, except that both sides of the first card are colored red, and both sides of the second card are colored black. And one side of the third card is colored red and the other side black. Okay. The 3 cards are mixed up in a hat, and one card is randomly selected and put down on the ground. If the upper side of the chosen card is colored red, what is the probability that the other side is colored black? So we denote like this. So RR represents the first one, BB represents the second one, and RB denotes the third one. Respectively, the events the chosen card is all red or black, or red and black card, right? Also, letter R represents the event that upturned side of the chosen card is red. Okay, then, so this R is already happened, right? Because this is a condition. The chosen card, the upper side of the chosen card is colored red. So that's our R. Then the desired probability is this, because we want to find the other side is black. So basically we want to find the third card. So probability of the upper side is already red, and the probability of the card is the third one is the probability of the intersection of those two divided by probability of R. So probability of intersection of those two, look at the numerator, is the probability of being the third card multiplied by probability being the third card and the upturned is red. So red. Then divided by the denominator P of R. We have these 3 cases, right? So then turn it up is red. So the card being turned up is red. We have these 3 cases. We use these 3, probability of the first card, probability of the first card being red, 100%. Probability of the first card, 1/3. probability of the third card, right? Third cards are the red and black, and the probability of third card and the upturn is red. That's half, right? That's 50%. Then probability of the second card is all black, and all black and cannot turn to be red, right? That's why it's a 0. So probability of the third card is 1/3, and probability for the third card to turn up to be red is half, because it's only black or red. Probability of the first card turn up to be red is 100%. Probability of getting the first card is 1/3. Probability of the third one is 1/3. Probability of turning it up to be red is half. So this one is 0 because it's all black, no red. In the end, we calculate, we get 1/3. So this is a good question. This is a good example. Anyone has any questions? Yeah. So the comments is saying, you know, a lot of probability questions is not intuitive at all. All right. Let's see. Let's see this example. A new couple known to have 2 children has just moved into town. Suppose that the mother is encountered walking with one of her children. If this child is a girl, what is the probability that both children are girls? So let's name some events. So G1 means the first child is a girl. G2 means the second child is a girl. G means the child singing with the mother is a girl. Yeah. That's already given, right? So the child walking with her mother is already a girl, so that's G. We denote B1, B2, and B. So B1, B2, and B denote similar events, except that a girl is replaced by boy. So basically saying B1 represents the first child as a boy, B2, second child is a boy. B is saying the child walking with her mother is a boy. So now the desired probability of the child walking with her mother is a girl, already known, and that is 2 children are girls, so G1, G2, right? So which can be expressed as this. That's the intersection of those 2 events. So G1, so the first child is a girl, second child is a girl, and the child working with her mother is a girl, right? Intersection. Divided by probability of the child singing walking with her mother is a girl. Then, okay, so this can be simplified, right? This can be simplified. If the 2 children are girls, you know, the child walking with her mother has to be a girl. So that's why we can ignore this G. So probability of the first one is a girl and the second one is a girl divided by probability of the ones being seen is a girl. So the probability of the ones being seen is a girl is, let's see, 2 cases, right? So the first one is a girl. So because given the first one is a girl already. Are we given the first one is a girl? The mother is encountered walking with one of her children. If this child is a girl, okay, so this one is given as a girl. So G, right? So first child is a girl and second child is a girl, and first child is a girl, second child is a boy. First child is a boy, second child is a girl, and the first child is a boy, second child is a boy. We have these 4 situations. Then if 2 girls, if this, right? given that two children are girls, you know, the girl to be seen is a girl, well, that's 100%, right? Given the first child is a girl and second child is a boy, what's the probability of the girl to be seen? And given the first child is a boy, second child is a girl, right? What is the probability of a girl to be seen? Given two boys, well, there's no girl to be seen, right? So we then, you know, plug in all those numbers. Right, that would be 100%. That would be 0%. Right, that's here. This one becomes this divided by this. So two children are both girls. That's 1/4 because we have 4 situations. We could have a girl, 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 boy, boy, girl, or boy, boy, right? So that's 1/4. Then the first one is the same as the numerator, is 1/4. And then this one, so this we don't know probably. Okay, so also for the first child is a girl, second child is a boy, that's 1/4, right? That's 1/4. Then given that, what is the probability of the girl to be seen? And then also the first one is a boy, second one is a girl, that's 1/4. Then what is the probability of a girl to be seen? So left with those. So now the answer depends on whatever assumptions we want to make about the conditional probability. That this child seen with the mother is a girl, given the event. The first one is a girl, second one is a boy, and the child seen with the mother is a girl, given the event. Yes, that's these two, right? That's these two situations. For instance, if we want to assume on the one hand that independently of the genders of the children, the child walking with her mother is the elder child, or if it's the elder child, right? If it's the elder child, this one would be a girl, then this one would be 0. With some probability P, or with some probability of P, okay, then we can simplify the above one to be, so then probability for this one would be P, right? There will be 1 minus this, the first one is a boy, second one is a girl, which is this one. Then in that case, we will get a half, right? Because we put it in, we have 1 plus 1, that's 1/2. On the other hand, if we will assume that if children are 2 different genders, then the mother would choose to walk with a girl with a probability of Q independently of the birth order of the children. Then we would have probability of the first child is a girl, second child is a boy, and the probability of the first one is a boy, second one is a child equals to the Q. You know, we can plug in, we get a 1 over Q plus Q, 1 over 1 plus 2Q. So this basically saying is, so we derived this formula. Then, you know, the rest just depends on the assumptions or the given conditions. Okay, let's see this example. A bin contains 3 types of disposable flashlights. The probability that a type 1 flashlight will give more than 100 hours of use is 0.7, which is 70%. With the corresponding probabilities for type 2 and type 3 flashlights being 0.4 and 0.3, respectively. Suppose that 20% of the flashlights in the bank are type 1, 30% are type 2, 50% are type 3. A. What is the probability that a randomly chosen flashlight will give more than 100 hours of use? More than 100 hours of use. B. Given that a flashlight lasted more than 100 hours, what is the conditional probability that it was a type J flashlight? Or J can be any 3 types. Okay, let's say A. Denote A as an event that flashlight chosen will give more than 100 hours of use. And let Fj be the event that type J flashlight is chosen. So we want to compute P of A, right? Probability of A last 100 hours. So we condition on the type of flashlights to obtain probability of A equals for the first flashlight, for the second flashlight, second type, and third type, and over the condition, right? Let's just plug in those numbers. And B, the probability is obtained by using Bayes' formula. Bayes' formula. Because this is the, you know, given the event already, you know, they can be used for 100 hours, more than 100 hours. What is the probability that it was a type 1, type 2, or type 3? Right. So probability of type 1, type 2, type 3, and given, you know, they can be used for more than 100 hours, equals to probability of the intersection of those two divided by probability of A. And the intersection of the probability of the intersection, we use again this probability condition. That's the probability of the flashlight, right? F1, F2, F3. Because we only have 3 types that will be wanted. Then for the given, you know, first flashlight or first type, second type, or third type, and it can be used for 100 hours. Then just plug in those numbers, given numbers in the context, right? So get those 3 numbers. So hence, for the first one, we get this one. For the first type, for the second type, for the third type, we get all those different numbers. All right, I think I'm done talking. And okay, so next time we're going to talk about independent events. Anyone has any questions? So we learned a couple of formulas. All right, so today is Bayes' formula. And one even before Bayes' formula, one of the propositions. I need also to remind myself. Yeah. Let's see. Yeah, 3.3 is very long, but it's very important because Bayes' formula is so famous. It's so useful in probability theory. Okay, if you have no questions, you are free bird. I think everyone probably very tired. Because probability is a different mathematics, right? It's not too much of calculation, but a lot of decoding. Okay, if you have no questions, you are free bird. So let's quit for tonight. If you do have questions, I'm here. I'm happy to talk to you about it. And right, prepare to present next time.